Okay.
Okay.
So, yeah, so, right, you'd asked about whether I could talk about some category of motives, some kind of motives. It's a semi-simple category, and that's exactly what I wanted to talk about.
Okay.
So James Milne has written lots and lots of stuff that I'm getting to like to read, and he has a number of papers on motives, but he has a kind of quasi-expository paper on motives, and it's called something like Motives Over Finite Fields, and that's what I've been reading. So you can define motives starting with varieties over any field, but he's just talking about over finite fields here mostly. And so that's what I'm going to do.
Okay. You said you could do motives over any particular field, but if you do it over the rationals or something, is that equivalent to like doing it in general, or there's no in general? You don't even have to answer that question.
I don't even know. Yeah.
Okay.
I don't know.
Okay.
Somehow it seems like both a lot of the interesting stuff, like about the vague conjectures, involves the finite field case, and also the finite field case seems to be the best. Well, no, I won't say it's the best understood, but it's well understood in chunks. And so, yeah, I'm just gonna. That's all I attempted to try to understand, and even there are different kinds of motives, and so I have to tell you what kind of motives I'm talking about. And the rough.
Can I interrupt?
Sure. Yeah.
Just should I parse that as motives over some particular chosen finite field K or something like that?
Yeah. So I'm gonna. Yep. So that's what we're gonna do. We're gonna fix a finite field. And
which I can call F sub Q or something?
Yeah, I'll call it F sub Q because the number Q will show up a whole lot.
Okay.
So I want it to be known to us as Q. So then there's still different concepts of motive. This could be like an endless quagmire, but I want to focus in on the type of motive that we really want. So, I mean, just to steer towards it a little bit. So, I mean, there's one kind of distinction that people like to talk about. There's several different distinctions going on. So one is like the difference between pure and effective motives. And I'm gonna do pure motives, and that means basically
can I sure as hell would have guessed if you asked me what was the opposite of pure.
Sorry,
I said mixed.
Sorry, I meant mixed. Yeah, you're right. Thanks. Sorry. Yeah, effective motives will show up as part of the pure story.
Okay.
Right.
Okay.
Yep. I'm going to do pure, and that's basically you sort of start out by thinking about smooth projective varieties over finite fields, over FQ in this case. And we're going to start with them, and then we're going to do stuff to get this category of pure motives. So mixed motives would involve more general kinds of varieties.
I mean, I already have to stop and think about whether I'm sufficiently happy with the concept of smooth projective varieties over a finite field, over F sub Q. I guess maybe, but it's possible I may have to ask more precise questions about that later, but sounds pretty reasonable.
Yeah, I, to some extent, fake it. When you read the definition of smooth variety over a finite field, you get into some.
Well, I also fake it with over, and
Well,
varieties.
uh-huh. Yeah, so let's not worry about it too much,
Right.
because there's like tons of things to worry about. One thing
Sure.
that we can worry about without knowing too much is that if you have a smooth projective variety over FQ, you can talk about its points over FQ, but you can also talk about its points over any extension of FQ.
Right, right.
Which are,
that's a good point, yeah.
The fields FQ to the N. And the Weil conjectures are like a formula, a kind of formula for the number of points over F sub Q N.
Sounds reasonable, somewhat reasonable, yeah.
So that's that's all we need to know about that. So the main thing is we're going for pure. But then there are other decisions to be made. So I mean, I could review the construction of the category of motives in various amounts of detail, but one thing that I'm sure you already know, because we've talked about it, is, at least you sort of know, is that defining a category of motives requires choosing an equivalence relation on, well, they call them like algebraic cycles, which are basically like subvarieties of a variety. And there are these different so-called adequate equivalence relations, which are the ones that you could choose from to define.
Right, I've got that vague idea, and I'm expecting that we're going to have a very extremo such adequate equivalence relation, because you've already hinted at this, we've already hinted at this, but
right,
making it be very extremo is going to, I'm saying extremo rather than degenerate, but it's going to be extremo enough that things are going to be pleasantly simpler than you might fear.
Exactly. So
simpler, although it may also have the feeling of being a toy thing that.
Well, it's
that we need
toy.
to.
Yeah, it's not really a toy thing, because it's even in the simplest case, we require an unproved conjecture to
okay, that's
get what to
that's
get
encouraging or discouraging in a way. So
yeah,
go ahead.
Yeah. So like you said, there's a kind of partial order on equivalence relations always, and so at the one extreme, which is like the hard extreme, like
you'd think that would be fine.
It is fine, yeah. The finest one is called rational equivalence.
Okay.
And this is sort of the one that Grothendieck wanted to use, you might say.
So that's sort of a distant goal.
Yeah, and so so that would be great to understand, but we're not going to. I won't get into it at all, I guess. Just in an attempt to like focus in on what we're actually talking about here.
Yeah, so we're going to the exact opposite extreme of the ambitious extreme.
Yeah. I'll just mention that there are a bunch called homological equivalents.
What do you mean? That it's ambiguous when you say homological equivalence?
Yeah. So there's like one for each homology theory. So one for each so-called Weil cohomology theory. So you can talk about well, in this particular game, since we have Poincare duality running around, because we're in a smooth setting, people like seem to pop back and forth between talking about homology and cohomology in a somewhat distressing way.
So it sounds like you're saying there's a forgetful map from Weil cohomology theories to adequate equivalence relations.
Yeah, that's right. So sorry, one for each Weil cohomology theory.
I mean, does that mean that the adequate ones aren't really adequate? That you need it to be super adequate, meaning you need it really to be a Weil cohomology theory? I don't know.
Well, I'll tell you. there's tons of stuff that's not known that's conjectured, which
Okay.
some of which I'll allude to. Don't expect that means I actually understand it. It's just like stuff I've heard. And then at the bottom, the coarsest one, which is the one we're actually going to use, is called numerical equivalence. So like you guessed, we're going to go for the coarsest one, and that's in some sense the easiest one to work with, which is why I'm able to report these results from Milne, and why Milne's paper focuses on this case. So you may know that given, I'll try to say what this equivalence relation is in words. You may already know it. So given, and again, I'm pretty vague about all of this stuff.
Sure.
But you can, given nice enough subvarieties of a variety, you can define their intersection number, which is sort of basically like counting points with sign, if they have like the right, I guess like if their codimensions, if their dimensions add up to the whole dimension of the big ambient space. So just like, you know, things intersecting like this.
Sorry. I just somehow missed something we were saying. But what are you talking about, this intersection? What?
I'm trying to define numerical equivalence.
Oh, trying to define for me numerical equivalence.
Yeah.
Okay.
And so I'm reminding you that there's this way you can calculate, you can talk about an intersection number of two subvarieties under certain circumstances. And so a cycle is a linear combination, formal linear combination of subvarieties.
Yeah.
And so you can talk about the intersection number of two cycles by making it be,
yes, by extending, yeah,
bilinearly extending it. And so then we say that two cycles are numerically equivalent if their intersection numbers with everything else are the same. So in other words, we're taking this vector space of,
I'm just trying to write that. Well, go ahead. Say what you're going to say.
I'm just going to say it in another way. You already
sure,
got
go
it.
ahead.
You take this vector space of cycles. There's this bilinear form on it called intersection number, and then you mod out by the so-called, I don't know if people call this the kernel of the quadratic form, the stuff of the bilinear form. And well, that modding out by that is the same as modding out by numerical equivalence.
Yeah, that's a good way to think about it. Let me just try to write something like that down. Mod out by kernel, so to speak, of intersection bilinear form. Okay, and this is all, right, this is all on algebraic cycles or something like that.
Uh-huh.
And, okay, so you said, I mean, we said, I don't know, we may have hit it near the fine extreme. We have the rational equivalence near the coarse extreme. Yeah, that's what I'm trying to just make sure that fine. If you look at the, it's supposed to be that if you look at the definition of adequate differentiation, you can see that the fine extreme really is rational equivalence, and the coarse extreme really is numerical equivalence.
Yeah, that's
okay.
Yeah.
Okay.
So then here's another little twist that I just can't resist mentioning, which is that one of Grothendieck's standard conjectures that he wanted to prove to get the whole machine rolling. One of his conjectures was that all these different kinds of homological equivalents are the same, and that they're all the same as numerical equivalents. So
that's
it's possible.
That's a standard conjecture?
That's one of them, yeah. Yeah.
That they're actually the same.
Yeah, they're actually the same.
As equivalence relations.
Yeah.
Well,
so that's like
that's a pretty strong conjecture.
Yeah.
Is this, I don't know,
I won't
is this called like the zeroth standard conjecture or anything like
you're
that?
gonna make
What?
They're called, oh no, you're gonna make me remember that. So there's like A, B, C, and D.
Okay.
And I don't really want to try to remember which one it is.
Okay, but this is good to know. I mean, if it's true.
Yeah, I think it's good to know.
Some standard conjecture.
For a long time, I was like wondering whether rational equivalence might also be the same, but I think it's actually known not to be the same. So I'm a little confused about like why. About like why it's different from the rest and what that means. But for example, I've read it stated in no uncertain terms that if you use rational equivalence, you don't get a, you get a category that lacks some of the properties that I'm about to tell you about numerical equivalence.
Say that again, if you use rational equivalence?
Yeah, you get a category of motives that's either not semi-simple or not Tanakian.
Or something, okay.
Yeah.
Okay.
So no one like came right out and told me that rational equivalence was known to be different from numerical equivalence, but that would follow from that. I mean, it's sort of funny because all the really interesting stuff I'm going to say about using numerical equivalence will rely on some other conjecture. So, which is not this one here, but nonetheless, modulo up to that conjecture, when we use numerical equivalence, we'll get a semi-simple category of motives, and it's Tanakian, and I've been told that that's not true for this rational equivalence version of motives. So it sounds
like one of the things you're saying is that rational equivalence is not associated with a vague cohomology theory.
Yeah,
no, not necessarily. Let's see.
Well, I think that would follow from what you're saying. It just makes me nervous. It makes me nervous because I've heard it said that every vague cohomology theory factors uniquely through the category of motives that you get from rational equivalence. So that almost makes it sound like it's the universal object in those, it's like the initial or whatever, one of those ones that come from vague cohomology theories, but it may not itself come from, but that doesn't really prove that it comes from a vague cohomology theory.
I mean, maybe maybe this standard conjecture that you were talking about, maybe it's really parameterized by vague cohomology theories. Maybe each one of them is conjectured to be equivalent to numerical equivalence.
Yeah, that's true. That's true. I mean, the conjecture just says that they're all the same as numerical equivalence, but I could imagine someone proving it for one of them and not yet knowing it for the others. Mm-hmm.
Well, okay, yeah, there's things to be straightened out here. It sounds like you're saying there's a universal something that isn't a something. But
that sounds like what they're saying. Yeah, I know. That irritates me.
Things like that sometimes happen, sort of. But
it could be that the definition of vague homology theory is just like a little bit too fine-tuned to allow its universal one to be one. Like what's the universal finite cyclic group or something like that.
Yeah, no, that's right. That's well, but it would be good to eventually clarify more about what's going on.
Yeah, Yep.
But okay, this is already very helpful. Go ahead.
Okay, so I'm feeling that you're happy enough, just enough. All this is just like a good enough kind of explanation.
Yeah.
Good enough, happy
Adequate.
with the idea of what?
Adequate.
Adequate. Okay, that's right. An adequate explanation of numerical equivalence. So then there's like another thing that I could do in different amounts of detail, including none, which would be explaining like how, given this equivalence relation on algebraic cycles, you define a category of pure motives. I could like sketch it out super sketchily if you want.
Well, I do want this, but what are the alternatives?
Well, one alternative is just that I know you sort of have read a little bit about this. So one alternative is I could just like say, not explain it at all, and just say, okay, now that we've picked this equivalence relation, we get this category of pure motives, and hope that you're like happy with that. But
the
opposite extreme would be like
right. One of the
long
alternatives
and
is
boring lecture on exactly how it works.
No, but I wasn't asking. I mean, I know that one of the alternatives to discussing this is not discussing this, but I was thinking, that there would be some compensation of discussing something else if we didn't discuss, because I really do want to discuss this. But it's not, I don't want to prevent you from going on to some other really interesting topic.
Yeah, I mean, the main thing, well, depending on how much time I have, it sort of varies. Yeah. But I mean, the thing I absolutely want to do is explain what are the simple objects, not what they are, but what the simple objects in the category of pure motives with numerical equivalence, what they're parameterized by, what they're like. That is like, I'll say what they are with quotes around R, in the sense that, like, if I told you what finite dimensional vector spaces are, I would just say, well, they're dimension. That's all there is to them.
Yeah. I mean, that is almost all you need if it's semi-simple enough. You're just going to take
and that's all. And I can only say certain things about like how you actually get that result.
Oh, okay.
But I can definitely say exactly what the result is, and it's sort of cool because it's a fairly tractable thing when you're done. So that's like like with vector spaces, like it makes you happy when you.
Yeah. Okay, but let's think about this a bit. When I say this, I mean, let's think about the process. The first thing you asked about. I'm just trying to catch up on how well I understand what you're saying, and also sort of guess where you're going. After that, guess where you're going after that. So okay, so let me see. So you've got, trying to re-summarize to myself this thing about the kernel of the intersection form, bilinear intersection form. So let's see. So we've got, right. I'm trying to picture what these cycles are. Let me think. Cycles, what the hell? So smooth projective varieties.
I'm beginning to think I'm wanting to reimpose the no.
Well, but I mean, so it has something to do with smooth projective varieties and some kind of correspondences between them.
Yeah.
And massaging that to get some sort of category out of it, and perhaps being willing to massage it more to get it to be semi-simple or something like that. So let's see. I mean,
yeah. One thing, by the way, is we don't force it to be semi-simple. We
don't force it to be semi-simple. That's what you said.
Yeah. We do some stuff and then it's like still a non-trivial fact that it turns out to be semi-simple.
Okay, but what, is there sort of a priori some target for this thing? Do we know a priori that we're going to get an abelian category? Do we know a priori that we're going to get a category enriched over something?
We will get a category. Let me go through. Yeah. So let me go through the steps at a high level, meaning like not too sinking into too much detail. But like the first thing we do, you're right, is we like choose a field of coefficients, which is completely different from our other field.
And this one is often likely to be the complex numbers?
It could be the complex numbers. It could be the
rationals. Yeah.
Algebra. It could be the rationals. It could be the algebraic numbers. Yeah, algebraic. The what do we call it? The algebraic completion of the rationals. I'm getting a little confused about what I want to do, but I think I'm gonna. Yeah, so I'm getting a little bit confused about like what I need it to be. But I think I'm just gonna, sorry, this is a little bit annoying maybe, but I think I'm gonna choose, sorry, I should like check to see what we're allowed to do. I'd like to choose the rationals. I'd like to choose the rationals, but I may have to choose the, oh, I'll just choose the rationals. Okay.
Sorry for, okay. And I was doing a bad job of completely paying attention. What was you didn't say why the rationals? Just, but it is the rationals.
Yeah, just want to.
Okay. Okay. So I'm just trying to get here. So you're defining a pure motive category, and it's depending on this first field, which I don't know, I'm calling it the geometric field. Do you have a better name for it? It's the...
Whatever, I don't know, yeah.
Okay, and it's depending on that first field and together with an adequate equivalence relation. Right?
Yeah.
And then, and then it's also depending on this coefficient field.
Yeah. So this coefficient field, one of the things the main kind of thing we do with it is that instead of just like looking at integer linear combinations of cycles, we're going to look at combinations in this field. Combination coefficients in this field. That's sort of what, just like I mean, that
almost makes it sound like the adequate equivalence relation could relate not just to the first field, but also to the second field or something like that. But I don't have to worry about that. Okay, so the coefficient in this context means, roughly, it sort of means coefficients of the algebraic cycles.
Yeah. So then roughly what we do is we do this. So we like define correspondences. So like a correspondence, and I'm going to say from a variety X to a variety Y. And here I mean these smooth projective varieties over our finite field. So it's a span. It's a span of varieties. And then this apex is equipped with an algebraic cycle. Sorry, equipped with an algebraic cycle, by which I mean like a linear combination with these coefficients. So like with a Q linear combination of Subvarieties. I'm getting too worried about whether they are allowed to be non-smooth or not. The Q-linear combination of subvarieties of S. But these subvarieties have to have the right dimension. Actually, no, sorry, but then I want to mod out by the equivalence relation. Yeah, so how do you say that? Like with an equivalence, with a numerical equivalence class of these guys. Numerical equivalence class of these linear combinations of subvarieties of S.
Sorry.
Yeah.
I thought you were sort of describing this for an arbitrary adequate equivalence relation.
Well, yeah, I could, and then I would just cross this out. But I'm just trying to do the numerical. I'm only going to talk about the numerical one.
Yeah, but I was just worried that, maybe even when you're doing an adequate equivalence relation, maybe actually you use numerical equivalence in certain places. But no, this is just the adequate equivalence relation rearing its head. Okay.
Yeah, this is exactly where, this is the only place it rears its head in the definition of motives, is defining.
Can I think about this? Let me think about that. Let me think about this. An
I'm not quite done
cycle.
saying this thing yet.
Sure. Okay. Keep going. But I have some questions and stuff here. Go ahead.
Yeah. So basically, you want them to be like. So here's something that like confused me for like a month. So there's the category of motives, and then there's the category of motives op.
Yeah.
And you might think that there should be like a functor from the category of varieties to the category of motives.
Well, can I think? Don't tell me. You
Okay.
say it again. You might think that there should be a what? A functor from what? From
varieties to motives.
Okay. Let me think.
Or to correspondences. Let's not go all the way to motives, but we're building. There's going to be a category where the morphisms are these guys. And I was saying,
yeah, I was expecting. Well, I was half expecting at least something like that, but I didn't. I mean, I was also somewhat agnostic about how self-opposite or non-self-opposite this category of motives was going to be. And it sounds like you're sort of getting into something about that, and that if it's not self-opposite, then you would have to worry about which way an embedding of the maps, which way to interpret a map as a correspondence.
Yeah, right. So I don't know if it's its own opposite or not, but what I know is that because they're trying to get the category of motives to be something sort of like a universal co-homology theory.
Yeah.
They want to stick in an op in so that that eventually you get a map from varieties, well, to correspondences, in fact, and then eventually to motives that's contravariant. So like when you look at this thing here, how you can think of spans as, you can think of morphisms as special spans.
Sure.
But here, like the way you think of it here, just evilly, the way you think of it is that like the morphisms are sort of the backwards pointing spans. In other words, the spans where the right-hand leg is the identity. So this like confused. It's sort of, in a way, it's like not that big of a deal, but it confused the hell out of me. So like
sure.
So what it confused the hell out of me is that basically they want these subvarieties of S to have the same dimension as Y.
Okay, can I think about that? Can I think about that?
Sure, yeah.
Okay, right. So that's okay. So that is certainly breaking the symmetry, breaking the left-right symmetry.
Yeah.
So, all right. Let me try to get this. Let me try to get this to understand. So, okay, so correspondence. Span. Together with a equivalence class of coefficient combination subvarieties of the apex of the same dimension as the target. I mean, this seems really fun to think about. So, you know, I'm not sure how much I'm going to have to stop and think about this here. Let's see. I mean, this is already so interesting. Let's see. Correspondence is a span. So, I mean, right? It is just a convention whether you do this left right x y or right left y x. But this. Yeah, it's not surprising if you have to be subtle about the convention.
Yeah, so I don't even know like how much the convention affects whether the category is semi-simple. So like finite dimensional vector spaces is equivalent to its op. Finite dimensional representations of a group. Is that equivalent to its op? I think it might be.
It's very close to. Yeah, I mean, you're talking about these semi-simple things?
Well, yeah. I mean, if it's semi-simple, then finite, then it might be. Yeah, so it could be that like by the time they get around to proving that this category is semi-simple, that maybe then you know that it's equivalent to its op.
But in the more serious non-simple semi-simple case, it could be that it's just blatantly different from its opposite or something. I don't know.
And also I'll just again remind you that the proof that this one that we're shooting for is semi-simple is reliant on a big number theory conjecture. So to like work with it before you know that conjecture is true, then you can't, I think maybe you can't assume it's semi-simple yet. So I've decided I'm going to go completely go along with like accepting all, what do they call them? Relative results? No, what do they call them? Conditional results.
Yeah.
And that's sort of that's the attitude that Milne takes. He says at some point he assumes a big conjecture, which I'll tell you about, and then proceeds from there. So since I'm just trying to understand stuff, I'm going to like go for being optimistic. And so maybe if I go for being optimistic, then in the end, this thing winds up being the category of motives is is equivalent to its op because it's semi-simple. But anyway, but people always stick this twist in here, and it just like confused the hell out of me for a while. So that's the only reason I'm mentioning it. I don't know if it's actually helping you at all, but at some point you might run into this.
All right. Let me think about the geometric intuition of this. Let me think about the geometric intuition. Of this dimension constraint. Let me think about that. So.
Oh wow! Sorry, I don't think I even said this right.
Okay.
I'm sorry. I probably didn't say this.
Okay.
The way, at least it might be right actually, but I didn't say it the way they say it.
Yeah. How do they say it?
So sorry. I should probably say it the way they say it. Probably because of all this gunk.
Yeah.
The way they actually say it is they say like, don't bother thinking about all spans.
Yeah.
Just think about the product span.
Ah, okay, yeah, okay. That's what I was wondering about. I was wondering about whether we should just do that.
Yeah, that's actually what they do. I want to think it. Yeah, so I want to think about it in terms of spans, but
okay. Let me write something down about this because this is. But boy, this makes that dimension constraint even sharper, more interesting. Let's see. Let me think.
Sorry, I screwed that one up. Yeah. Okay. So it's really this. It's like the linear combination of subvarieties is like the true apex of the span, and that this product is
right.
just sort of
Right. That's what I was. Yeah, that's what I was.
Ambient thing that it's floating around in.
But it also does really look like they're trying to decategorify.
Yeah. I mean, we're gonna only get when we're done, we're just gonna get a category. So we're gonna.
Yeah, but it does look like there's something here that sort of wants to be more than a category, but it's being decategorified. And maybe you hinted that Vygotsky or something did kind of think about undoing some of the decategorification here. I'm not sure if this was the decategorification.
For mixed motives, people were like completely were stuck at some earlier phase of the operation of even like figuring out what the right category was.
Yeah.
And he went ahead and sort of got a derived category approach. So he was sort of undecategorifying.
All right, I'll have to think about that. But so, maybe, go ahead.
So maybe we should, so maybe at some point we should think about this again, like try to.
Right, I mean, this does look like a decategorification of some more categorified notion of spans.
Yeah, that's right. Because I mean, I haven't even said like how we're going to get the category, but the first thing we're going to do is we're going to work with like, well, maybe it's built into this. Yeah, it's built.
I mean, when I say that it's a decategorification, I mean that in some very loose sense. Not necessarily that it's obtained by some well-defined decategorification process, but that it's morally intended as a decategorification.
Yep.
Yeah.
So,
right. Okay, but let me still think about the dimension thing. Let's see.
Just this is probably, assume this is obvious to you, but if it's not, I'll tell you. So, I mean, if you just had a map from X to Y, sorry, if you had a map from Y to X, if you had a map from Y to X, you would do the.
Don't tell me. Can I think? Don't tell me.
Okay.
Don't tell me.
Yeah. Okay.
Well, I mean, then you would take the graph as the cycle or something like that. You would take this the cycle that just consists of the graph of that map.
Right.
And you would do something with that.
Yeah. Yeah. So the graph of a map always gives you a span. And so the only thing that we're doing that's like a little weird here is that we're using a map from Y. We're taking the graph of a map from Y to X to get a correspondence from X to Y. It's just like some convention flip.
All right, by the way, just to get out of my system some comments that I don't want to talk about today, I just want to say that this idea of correspondences really shows up in an interesting way. Not necessarily the details of this definition of correspondence, but the general idea of correspondence really shows up in an interesting way when you think about stuff sort of like geometric quantization of compact Lie groups and stuff like that.
Oh, sounds fun.
So back to where we are here. So okay. So yeah. Okay. Let's see. So okay.
Okay. Yeah. I'm slowly adjusting the notes on my slide to match what.
Sure.
To match the reality.
Sure.
So it's a numerical equivalence class of Q-linear combinations of subvarieties of.
Oh, can I think? So
yeah.
Graphs of maps are notorious for, actually being just isomorphic to the domain.
Yep.
Yes, right? I mean, when you talk about, right, the graph of a map is really just a copy of the domain.
Yep.
And it's embedded in the product by the identity projection and the map projection.
Yep.
Projection, not sure that's the right word, but I guess it is the right word. And so this now really is sounding like a mild generalization of that. In other words, instead of being a map, which would mean that it was actually isomorphic to, let's see. It's like, I mean, it feels like it's just defined on coverings or something like that. It's, right? I mean, am I saying that right? Wait, no, okay, don't tell me. Sorry. Let me think about that. No, it's not defined on coverings. It's defined on more like open, no, let me think. Of the same dimension, let's see. So let's see. I'm trying to picture this algebraic cycle. Actually, I'm trying to picture the terms of this algebraic cycle. So these subvarieties, those subvarieties, they map down to Y.
I guess I could draw one if I was like doing real algebraic geometry. So like I could do X and Y could be lines and the cycle could be like a circle. This is a very symmetrical example.
Sure. Boy, this, for some reason, your example reminds me of something I've thought of, but I can't remember what it was. But see, right at the moment, I'm actually thinking, instead of thinking in terms of this subvariety being the same dimension as Y, I'm trying to think about the nature of the map from this subvariety to Y. You know, I'm wondering if that should be having finite fibers or something like that. Or, you know, right? Right? I mean, you could have, am I saying that right? Is that automatic? I'll have to think about that.
Yeah, it's not automatic. I could have taken this line. I could have like taken this line here. And then when I map it down to Y, it has the whole line's getting mapped to a point. But one of the kind of things
but nevertheless, it is the same dimension as Y.
Yeah.
But right, you see what I'm saying? That's like kind of weird, right? It is the same dimension as Y, but it seems like for a very accidental reason. But you know what I mean? By sort of compensation of error. It's just got that one big fiber that would be the same size as Y.
Yeah, I don't know how much people are able to like tweak things under numerical equivalence, but you know, it is, I think that this guy here would be like numerically equivalent to something that was like more.
That's a good point. That's a good
like
point.
This.
More transversal or something like
that.
So
I think that's sort of the goal of that kind of equivalence relation in part, is to sort of be able to perturb things to make them more generic.
That's interesting. That's interesting. That's interesting.
I want to go on.
Yeah, that's interesting. Okay, go ahead. But this, these are good integrations. Go ahead. Go ahead.
So, okay. Okay, well.
Yeah, I really have to think about that perturbation, transversality stuff. Go ahead. Go ahead. Go ahead.
Yeah. So.
General position. Okay, go ahead.
Yeah. Yeah, it's connected somehow to like all the old themes in algebraic geometry of general position stuff. Yeah. But I don't understand that terribly well.
Yeah.
So let's just say that, let's just pretend it's true, because I think it is true, that like we get a category with these correspondences as the morphisms. So there's
I just want to make another interruption comment. I just have to say here.
Okay. This
whole thing that you're describing here, it really, really reminds me of crazy stuff that Louis Crane used to talk about. You know, he wasn't, it didn't sound like he was talking about algebraic geometry, but he used to talk about things like this in.
Yeah, I don't remember that.
In geometry.
Huh.
And when I say talk, I mean literally talk. You know, I only really saw him at a conference like once or twice, I think.
Was he talking to you, or was he giving a talk?
No, he was talking to a bunch of people who were gathered around, and some of the, you know, really sharp, perhaps graduate students or perhaps professors or something like that, were really sort of questioning him about what he meant, because it sounded like he was saying kind of crazy things, but maybe they weren't that crazy. I mean, they weren't that crazy, but they weren't that crazy. But it was the kind of thing people were questioning him on the details. But okay, go ahead.
Okay, so we got a category with these correspondences as morphisms. Let me just assert, where the composition is this sort of spanny or matrixy type composition. Okay, but it's not good enough yet. So we do two things to it. So
sorry, I'm trying to pay attention. Is it possible you can call back that page for a moment? Yeah. Okay, I'm just trying to catch the last thing you said. You just kind of said that we already got, probably we've already done enough to get a category. You would have to check to make sure that you understand how to compose the correspondences. But it's going to give us a category already, but it might not be quite ready for prime time yet.
Right.
Okay, go ahead.
Yeah. Oh, and one thing that I will need, I guess, is that this category is vect enriched. It's because you can add these, you can take Q-linear combinations of these
coefficient vect enriched.
Yeah. So it's vect sub Q enriched.
Okay.
So we're getting.
Okay. Well, I mean, I should write down a note about that. So
I'll just say this category is Q linear.
category. I'm ready. Coefficient enriched. Okay, go ahead.
Okay. So then they want to massage it to make it better in their notion of better. So then we Cauchy complete it in the enriched sense.
Sure, that's pretty straightforward.
Yeah, they make heavy weather out of that.
Say it again. They do what?
They make heavy weather out of.
I'm not sure I understand that expression. What? They make it sound impressive?
Maybe that's like a British expression. It means they make it sound like a big deal.
Okay.
But because they give like a concrete description of the Cauchy.
Oh, sure. It's actually fun to give very concrete descriptions of.
Yeah, no, it's probably good to do. I mean, it's probably good to do in order to like work with it as well as fun. But yeah.
Yeah.
But okay, that's step 2. This is called. So this.
I mean, I'm imagining that, that the concrete way to do it is you make the objects to be idempotents, but then the morphisms are these other idempotents, writing the original idempotents or something like that.
That sounds right, yes.
It's been a while since I've thought about it, but I did think about it. Go ahead.
Yeah, so this thing here, so this thing that we get, this new category that we get has a name. It's probably good to know. So we get the category of effective pure motives.
Okay, that's the effective pure motives.
And if you want to be like super careful, it's like effective, pure, numerical. No, you don't need to say effective and pure. Forget it. Effective is, well, maybe you do. I don't know. I don't know if, but yeah, they probably do. Numerical motives. So numerical just meaning because we're using this numerical equivalence relation. I'm not going to say all this stuff all the time, but
sure.
There's so many knobs you can turn.
Sure.
You have to sort of be careful when you're reading stuff.
Sure.
Okay, so that's pretty nice. But then,
sorry. What about should I be reading any cultural thing into effective, other than the fact that it was maybe originally a French word or something like that?
I don't really know.
Aren't there effective? What am I trying to think of? What are other things that are called effective? Effective equivalence relations. Effective equivalence relations. Effective divisors. I don't know. I'm trying to remember other words that are called, other things that are called effective, and wondering if they're related to this, or if it's just that certain people use the word effective a lot for various different things.
Yeah, I don't know. All I know about this effective is that it's like contrasted. It's like a contrast. It's used in contrast to the more general things we're about to get in the third step.
Okay.
So let me tell you the third step.
That's interesting.
So then,
that's interesting. Yeah, go ahead.
So then, formally, what do we call it? Formally, tensor invert. I guess I will just say that tensor invert the Lefschetz motive.
Okay, I'm going to stop and think about that. Sorry, can you remind me of the short version of the story of what the Lefschetz motive is in terms of, what specific varieties it tends to correspond to? Well, I can't remember whether it's more like the affine line or more like the projective line. Or...
It's like the affine line. So the way it works here is that when we do this Cauchy completion,
sure.
The projective line has this map from it to itself.
Sure, yeah. Okay.
It's idempotent. It maps it all down to a point.
Sure.
And so when we
just split that,
split that idempotent.
Sure, just split off the point, yeah. So, see this, there's very suggestive things going on here. Well, okay, but one of the things that I need to clarify is, when you say tensor invert the Lefschetz motive, if you want to do that in an optimal-ish way, you should really try to clarify what is this process that you're really doing. In other words, you may want to say that you're working with for example, a nice thing would be if you were working with the nice two rigs, the symmetric monoidal locally presentable categories. And the tensor inversion process is just a matter of believing in the. So first I'd have to check whether we're really in that belief doctrine, whether we really are getting a total two rig. At the level of the effective pure motives. But if you were, then at that point you could just say, let's just believe in the tensor invertibility. There are subtleties to worry about, but basically it should work out very nicely. You just say, let's just believe in the tensor invertibility of the Lefschetz motive, and that would do things automatically rather than having to do it by hand or anything like that. And there are probably other doctrines that non-belief doctrines where you can do that same thing too, although it might be more annoying to deal with.
Yep. But can I say two things about that?
Go ahead. Yeah.
So one thing is that I feel that like the way we've set this up so far, we're not getting a co-complete category. Because we didn't do anything to make those like arbitrary co-products, for example, be there. So I feel that what we're getting is it's at least what do you call it? Like an absolute two rig.
Okay. Then yeah, you could possibly do it at that level too. At the level of absolute two rigs, you might very well be able to nicely define what it means to formally tensor invert an object. That's a good point.
And then another little thing that doesn't actually matter yet, but it does matter, is that there are two different important symmetries on this category.
Yeah.
Can I think about that?
You're talking about symmetries of the tensor property.
Yeah.
Can I just think about that for a moment? Just think about that for a moment. Symmetries. That's interesting. You make it sound like there's some sort of balancing there or something like that. But
well, let me tell you a bit about it.
Well, go ahead. Yeah.
So I'm very confused about like which one is. So they start with one symmetry, and then they say, "Oh, but this isn't so good, so we'll change it to this other one."
Yeah.
And I get really confused about which one is the good one and which one is the bad one.
Yeah.
But the difference I sort of understand. It's just like the fact that graded, like n graded vector spaces has two symmetries, the one with the minus signs in there and the one without.
Okay.
And
okay. Yeah,
and
yeah, that sounds very plausible. Yeah.
And I have the feeling, I'm really confused.
Yeah, I mean, that makes a lot of sense. Yeah.
I have a feeling that they start with the one that has the minus signs in it. And then they say, oh, but then we get some objects that have negative dimension, like the trace. They can define the trace of the identity, and it can come out to be negative because it's like an Euler characteristic kind of thing.
Yeah.
And then they say, oh, but then if we use that symmetry, then we can't get a Tanakian category, because in a Tanakian category, the dimensions of objects are always non-negative. They're always natural numbers. And so what they do, which to me seems a little silly, what they do is they say, okay, well, we'll just change the symmetry by, I think it's, they get rid of the minus signs that were there. And so then they get a new category, a new symmetry, and same category, new symmetry, same monoidal structure, just a new symmetry. And then now the trace of the identity of any object is greater than or equal to 0. And then they say, okay, good, now it's a Tanakian category. It can be the category of representations of a group. I have a feeling that this is because they weren't like thinking enough about categories of super representations of groups, and that they should really be talking about representations of groups on super vector spaces.
Yeah, it could be. I'm sympathetic to that.
Yeah, but anyway, so there is this issue.
Okay.
So when you started talking about symmetric, monoidal, locally presentable categories, I just had to mention there are these two symmetries available, but they're very similar. And I don't think it affects at all the issue of I bet it doesn't affect the issue of tensor inverting an object.
It sounds like it probably doesn't affect it, but I'll have to think about that too. Yeah. But yeah, you're sort of right. You're making the point to me that there's a lot of details to consider here.
But I basically think you're right. I mean, I think it would be doable and good to try to take some of this stuff and do it in a more explicitly two-riggy way. And I bet that your ideas on belief doctrines should apply to this. I don't think it's supposed to be like some super horrible, sneaky situation. I think it's supposed to be like a pretty nice situation where those kind of ideas should apply.
Yeah, it could be, but the absolute viewpoint also can be very nice. But what am I trying to say? So there's some interesting stuff going on here. So remember how we had a relatively long, inconclusive discussion, perhaps partially here and partially in email, about very vague ideas that I had about the idea that formally tensor inverting the Lefschetz motive, when you're inventing motive theory, that strikes me as being potentially analogous to the creation of the stable homotopy category, where you can talk about formally smash inverting the is it the one sphere? No, yeah, it's the one sphere. Formally smash inverting the one sphere, because the zero sphere is already the unit object, so it's of course invertible. We talked about that potential analogy. And we mentioned all sorts of glitches with that analogy. So for example, that when you're doing the formal inversion of the circle S1, formal smash inversion of the circle S1, it probably works out best if you do that in an infinity category context, Whereas here, you know, people, perhaps especially Grothendieck, have gone through a lot of trouble to make it so that you're not dealing with infinity categories here. You're dealing with categories by, you know, means of a whole bunch of perhaps tricks that are going on here. So there's still this idea of, there's still this potential for an analogy there, but it's very unclear how the analogy might work out, partially because of, you know, issues about treating things as categories versus treating them as infinity categories, et cetera, et cetera, et cetera. But there's something kind of interesting going on here, which is that, what am I trying to say? Well, I mean, in this analogy, in this potential analogy, because I'm not sure how well it works out, but in this potential analogy where the Lefschetz motive is something like the circle.
Uh-huh.
I mean, we already played around with that.
Yeah.
You know, and it suggested, you know, maybe it's only off by a point or two or something like that. But it's, what am I trying to say? So the, you know, the circle is like a walking loop, obviously. It's like a walking endo. But the Lefschetz motive, which you kind of say is the affine line, my vague sense of what the affine line is in the motive world, and this had a lot to do with when I was staring at the definition of the well-known adequate equivalence relations, comparing rational equivalence to perhaps numerical equivalence or some other equivalence. And it sort of looks like what's going on is that the Lefschetz motive, the affine line, something like that, is perhaps being used as an interval object. So, I mean, right, there is,
Mm-hmm.
you know, the whole analogy may be screwed up, difficult to straighten out, but there's something there because, you know, in the stable homotopy theory world,
Mm-hmm.
we're talking about smash inverting something like the circle, whereas in the motive world, we're talking about, apparently we're talking about formally inverting something that's sort of like an interval object,
Yeah,
or something
mm-hmm.
like that. So, all right, the difference between, again, right? I mean, the difference between an interval object and a loop object, a circle object, is just some matter of tying up the loose ends. And the matter of tying up the loose ends is all tied in with this thing of splitting the idempotence and everything like that. So there's all sorts of technicalities that we don't understand yet, but there's still something very suggestive going on here that we should really try to get to the bottom of.
I want to get back on track, but I'll just mention one thing, which is that Voevodsky's approach to motives involves what he called A1 homotopy theory, which is a kind of homotopy theory where you use the affine line as basically as the interval object, as the thing to define homotopies. So
where should I put the one? Above the?
A super one. That's like
super, not below. A super one.
Yeah, that's like a standard term for like the affine line. And
okay,
if you want to really
A1 homotopy theory.
Yeah.
Perhaps.
So I don't recall seeing anything about him inverting A1, but I haven't read that much. I
mean, presumably you would start inverting it at the point when you start, or inverting it, or something very much like it, at the point when you start doing stable A1 homotopy theory, unless it's already stable. I don't know.
Yeah. Okay, so I want to march on.
Theory for Voevodsky.
It's just like a little.
And this is the affine line as interval object. Okay, go ahead.
Okay, so we formally tensor invert the Lefschetz motive, and then, okay, I'm going to jump to the next page here. I'm just going to say what we're done. So we've done these 3 steps, and then, and then we're done. And that's, so we get, so this gives the category of pure motives, pure, if you want to be cautious, pure numerical motives. So that's it. I mean, that's the category that we're going to talk about. Okay, so then Milne.
You just got to give me just a couple of minutes to think about this, because you're going to give like a basis for this category, and I just want to get some sense of what's going on here. I mean, right, because it is surprising. You're sort of threatening that it's going to be somewhat tractable.
Mm-hmm.
And we are making a lot of simplifications, numerical equivalence. But let me think. Numerical equivalence. Algebraic varieties, you see like pieces of algebraic variety, sort of, morally pieces, but they're.
Yep.
So, okay. So the affine things already are living here. They, because when the splitting, the Cauchy completion, produced the affine things as virtual projective things.
Mm-hmm.
So later on, when we get into mixed stuff or something, then we'll have to be worrying about singular stuff or something. But we've already got the affine things.
Mm-hmm.
They're just
they're
already available there. Okay, so we've got affine things. And we've also got, I'm just trying to imagine all these,
I don't know if we have
elliptic curves over finite fields. I'm trying to imagine all these curves where they belong. What were you going to say?
I don't know if we get all affine varieties out of this. We get the affine spaces for sure by taking products of the Lefschetz motive with itself. And then I don't know if
we're going to get an awful lot of affine varieties.
Yeah, we're going to get a bunch. The ones you can get by splitting idempotent. So
let's see. Okay, so these we fixed Q. So this is like just one Euler factor.
Mm-hmm.
Well, no, it's one Euler factor. Let's see, all the. I mean, you tend to get one Euler factor for each prime or something like that. And here we just have one prime,
right,
to worry about.
Yeah.
So it'd be like that. I mean, it would be fun to just quit here, just go home and try to invent this. But if you're dying to tell me,
I'm dying to tell you. Yeah, I'm just
okay. Go ahead.
Yeah,
go ahead.
Yeah. I mean, I'm not going to tell you why.
But it is just it's just surprising that or shocking, interesting that there could be something that on the one hand is. It's interesting if this really is tractable. It depends on what you mean by tractable. I'm not sufficiently taking all the courses into account for why it ends up being so tractable. But again, I'm just thinking of all the variety of different elliptic curves, or abelian varieties, all the weird things. They're all showing up there.
Yep. I want to go ahead. I want to go ahead.
Okay, go ahead.
I'm getting
well, but it sounds like it sounds like it's going to be going to have to do with some cohomology groups or something like that. Go ahead. Go ahead.
Okay. Anyway, so now Milne, to get anywhere, he now assumes a big conjecture. I don't want to even explain anything about it, but
okay.
But he assumes the Tate conjecture. The Tate conjecture implies some of the standard conjectures. It should be it's in bed with the standard conjectures. We've talked a bit about the
Say that again. What's the expression you used? You said
it's in bed with the standard conjectures. Yeah, so like you can get some, like it implies some standard conjectures, and maybe it's also true that like it and some standard conjectures imply other standard conjectures. I can't remember if that's true, but there are a lot of interrelations. Another thing I'll say is that like we've talked about the Hodge conjecture once.
Yes.
Yeah,
I think I still have a semi-reasonable idea what that means. There's some fine print.
So I've heard it said that the Tate conjecture is like the Hodge conjecture for non-zero characteristic for finite for non-zero characteristics. So the Hodge conjecture.
Are you saying it's like a special case, or you're saying it's an analog?
I think the Hodge conjecture is about complex varieties.
Okay, so say again, it's an F sub Q analog of Hodge conjecture, sort of?
Yeah. That's all. I mean, I'm just saying that just because it's like something that's easy to, it's vague, but easy to process.
Okay.
And it shows that like all these damn conjectures are all part of some network dreams, the same network of dreams. Okay, so then he can go ahead and do stuff. So then, let me give a name to this category of motives. There are lots of names, but I'll just call it like mote. And it's like motives, and it's like depend over FQ. I think he calls it mote of FQ. Okay, I'll call it that.
Yeah.
Okay. So then mote FQ is semi-simple is one of the things that he gets.
Okay.
And I
with
can't
some sort of somewhat explicit classification of the simple objects.
Yeah, so he winds up getting a very explicit classification of the simple objects, and also what happens when you tensor two simple objects, how it breaks up into blocks. It's all very beautiful. So let me just say what that is.
Okay.
So what is it? So, right. So, right. So it involves algebraic integers. So the first concept is that like a vague Q number it's an algebraic integer in the complex numbers. Well,
with a property?
Yeah, with a property. Maybe I'll say it like this. So because it's an algebraic integer, it's actually, let's think of it as actually like it's an algebraic number. So let's think of it as in Q bar, and I'm picking an embedding of Q bar in C.
Sure.
But of course that was somewhat arbitrary.
Well, can I think about how arbitrary it is? Let's see.
No, let's not talk. So the Galois group acts on.
Yes. Yes.
I mean, the embedding, the subset is not so arbitrary, but what I'm trying to say is arbitrary is that, sorry, the Galois group is acting on this Q bar. So this number is a number such that it and all its I'll just call them like Galois conjugates, all the things that you get.
Yeah.
Yeah.
Sure.
By acting on this. They all have absolute value. They all have absolute value Q to the M over 2 for some. Let me think about this a second. Let me think about how I want to say this. Yeah, for some integer M. So
for an integer M that does not depend on which Galois conjugate.
Right. Yeah. So yeah. So really, Milne talks about like a vague Q number of weight M.
Absolute value Q to the M over 2.
So that idea would seem weird, perhaps, if you hadn't if you hadn't seen the Weil conjectures.
Right, but it's already seeming somewhat okay because of vague rumors about the Weil conjectures.
So I sort of feel like reminding you about the Weil conjectures. I had just given you this little spiel.
Again, I mean, these zeta functions are like all one Euler factor.
Right.
And this Euler factor, I mean, we're sort of, the original Riemann conjecture has to do with this particular line. What is it? The line with imaginary part, something? No.
Yeah. So the way I like to think about
but this is actually now, we're looking at this as a circle instead of a.
Yeah. So the way I like to think about it these days is not so much in terms of the zeta function as in terms of just counting the number of points on the variety. Well, you're probably not going to like this because it's a formula, but so I had said like the Weil conjectures or the Riemann hypothesis part. Here I was taking Q to be P. I was just doing the case of a prime instead of a prime power. And then you can like look at the number of points over all the field extensions of it. And you get a sum of terms that depend on a kind of dimension. And then each dimension of your variety breaks up into these chunks called motives. and they contribute a number of points that grows like the q to some number over 2. So if q is, if the p here was the q that I'd been talking about, then these would be these alphas would be these vague q numbers. So the point is that we can count the number of points on a variety by chopping it up into motives, and the motives contribute numbers of points that depend on your extension of your original finite field. They sort of grow exponentially as your extension gets bigger and bigger, but they grow at a rate that's determined by the absolute value of this number alpha. And that k, so it's p, would be p to the k over 2, where k is some kind of, it's called the weight, but it's some kind of like dimension-like thing. And k, so, you know, like if I have an elliptic curve, it has a part that's like weight 0, a part that's weight 1, and a part that's so those are like real dimensions.
Yeah.
And so you get like k equals 0, k equals 1, and k equals 2. And for the elliptic curve, for the elliptic curve, like the formula looks, the number of points looks like this. And so you have
right.
The interesting part is this weight 1 part. That's the sort of mysterious part, because this alpha is not a positive number usually. It's a complex number. Right. So this alpha here is a vague q number. And so I'm just talking about that's the kind of number I'm talking about. And so where I'm leading towards is the idea that these vague q numbers are sort of, in some sense, almost all there is to these. In some very strong sense, it's all there is to these motives.
To these motives, yes.
To these type of motives that we've been just discussing here. So
yes.
Yeah. So okay, so that's a vague q number. Notice, by that way, when we invert the Lefschetz motive, we get these funny motives, like the inverse of the Lefschetz motive is the Tate motive, and that would be corresponding to m equals -2. So the projective line has m equals 2, because the number of points is just like,
yes.
Well, it's q plus 1. The Lefschetz motive has just q points, and the Tate motive, this formal inverse, in some weirdo sense, it has like q to the -1 points. So that's why we allow these integers here, is because we've inverted the Tate motive. If we didn't invert the Tate motive, there'd be a story like this, but we wouldn't have those negative powers coming in. Okay. When you chop an actual motive up into parts, you don't get the Tate motive showing up. You just get well, you
yes,
just get,
yes. But what am I trying to say here? That
when you chop an actual variety up into parts, that's what I meant.
Right. But what am I trying to say here? That so Q number, if it and all its Galois conjugates have absolute value Q to the M over 2. Now, Q to the M over 2, I'm not sure if you already told me all about this, but q to the m over 2. I'm just thinking about whether that is itself a Weil q number.
Yeah, it is.
And yeah, it is. And it seems like it's a rather important, very degenerate, very important, boring example of a.
Yep.
Because like you're saying those are the ones that are showing up in these very, very vanilla examples. Of varieties.
Yeah. So I want to march on because time is.
Okay, go ahead.
Time is also so. Because I'm almost done. So.
Okay.
So. Okay, here we go. So the set of isomorphism classes of simple objects in this category of motives that we're studying is isomorphic to, it's interesting, it's the set of Weil q numbers, but modulo the Galois group action. Modulo.
Right.
Q, whatever we call it. So that's it. Well, the other thing I could say without too much trouble at all is actually what's the tensor product structure on motives?
That I think I should shoot for homework because that seems really. I think I'll really understand that better if I do that for homework.
Okay.
I'll try to send you my answer by email and you correct my answer and so forth. Okay.
Okie doke.
But aside from that, you're done here.
Well, let's see.
Because I mean, this is great. I mean, but I'm really tempted to think about this. Let's see, Weil q numbers.
Yeah, basically done. One thing that I did that was fun, where I got a lot of help from people, was looking at some elliptic curves over the field with 2 elements. They're not that many different kinds.
Yeah.
And then I looked at what the Tate Conjecture says about there's one other big thing I want to say. Okay. I looked at like what kind of alphas you get, what kind of Weil q numbers you get from there. And it's quite nice because you're looking for numbers. Well, in that case, you're looking for numbers whose absolute value is just the square root of 2, because they're like these Weil q numbers where m is equal to 1. And so you get certain algebraic integers on that circle of radius square root of 2. And so it made it a little more concrete to me, at least in an example of like what kind of numbers these Weil q numbers are like, what they can be like.
This is all extremely interesting. Let me.
Sorry, there's one. Yeah.
Go ahead. Yeah.
Yeah. No. Let's just silently think a second. I had thought of like something else that's like incredibly cool. That's easy to say. No, I forget it. Oh, yeah. Yeah, okay, I can't, this is something that I have no idea why, almost know why it's true, but it's just too good not to say. So there's this other theorem that Milne claims is that you can maybe you know this, but anyway, I'll say it. I've had a feeling like you seem to be hinting that you know this, but never said it. So you can get all the simple motives as, I'll call them like summands of two kinds. So one is abelian varieties. So this is like, I love it because it means like there's some reason why I'm studying abelian varieties. And then two, there are these things called Artin motives. I think on an Artin, what's an Artin motive? I think it's just like it's like a zero dimensional motive. The motives have this dimension, which is which I was calling the weight before, which is this number m here. And so the Artin,
I mean, I have an idea of what an Artin
an Artin thing.
An Artin thing. I'm thinking like are they called Artin zeta functions or Artin L functions? And maybe Artin Galois representations or something like that.
Yeah, well, what an Artin motive is, it somehow comes from just comes from a finite dimensional representation of like the Galois group of our finite field.
All right, I'll have to think about that. But okay, so this list is finished now. It's just 1 and 2.
Yeah, that's it.
Abelian varieties.
Yeah, so that means that like the example of elliptic curves is like not so terribly, well, I don't know, depends what you think. It's not so terribly far from being pretty representative. I mean, well, that's sort of a lie. I mean, to the extent that elliptic curves are representatives of abelian varieties. But it means that we could like try to look at some abelian varieties and count the number of points on them and learn some stuff. Presumably, because they said the theorem this way, you get some Weil vague Q numbers that aren't the ones that you already got from the elliptic curves.
All right. So another thing that I should ask about you, and maybe I was halfway expecting you to say something about this if I hadn't tried to slow us down. But what am I trying to say? So you've given a pretty explicit description here of some kind of category. I have to check the details and see if it's, you know, I'd have to find out what Tanakian means and see if this is Tanakian and all that. But well, I guess that's one of the questions. Is this category that we're getting, is it sufficiently Tanakian in some sense, whatever the various definitions of Tanakian are? Is it sufficiently Tanakian that some sort of, you know, Tanakian reconstruction theorem applies to it? And again, I don't think I want you to tell me the answer to it yet.
Oh, okay.
But it sounds like you're telling me that it is interesting to reconstruct a group of some kind, of which this is perhaps the representations.
Yes.
And again, I don't think I want you to tell me in any terribly explicit way what that is. But I might not mind if you told me some jargon name for it, like if it's called, I don't know, you've been hinting at something called the motivic Galois group or something like that.
Yes, that's what they call it.
They call this thing.
They call this thing, and yeah, whenever you've got some category of motives that is the category of representations of some group. I mean, so there's these different knobs you can turn. You call that a motivic Galois group. Like one big knob you can turn is like replacing FQ by some other field here, and so that people definitely think about it for other things. But yeah,
I mean, I think it's also interesting to vary the other field. The coefficient field.
Oh yeah, that's right. That's true.
I mean, it sounds interesting. I'll think about what it actually amounts to. But all right. Like I say, I mean, I'm completely satisfied with this.
That's fine. I mean, I'll just tell you that I don't really know. Maybe I've known it and forgotten it. I don't really know the group offhand. So
okay, that's fine.
So it actually is a fun puzzle to take this description of the category together with the description of the tensor product, which you told me not to tell you, but the sort of obvious tensor product, and then like try to guess what the group is. So,
well, I mean, going by very naive, wild guesses, it's looking like some of the simple objects are not themselves tensor invertible. That's making the motivic Galois group sound non-abelian, which perhaps is to be expected. Or to be expected, to be hoped for, whatever. Maybe it's obvious, but let's see. So, yeah. Well, now, right, now you're also making it sound like it's fun to try to give something along the lines of a presentation of some K-theory ring of this category as a lambda ring or something like that. And perhaps try to massage that into a sketch of an absolute two-rig or a sketch of a total two-rig or something like that.
Yep. Yes.
So, I mean, I'm also already trying to imagine that, trying to imagine what kind of generators you might need here. Have to think about it. All right, is there anything else we should do before we quit for today?
No, nothing we need to do.
I mean, probably all sorts of questions I'm forgetting to ask, but I've got a lot of good stuff to think about here.
Yeah, I was really happy to learn this stuff and surprised that more people didn't seem to say this stuff. People seem to talk a lot about how mysterious motives are, but this makes them seem a little less mysterious, except of course for the fact that they need the Tate conjecture to prove this stuff. But the picture, I mean, I don't understand this. Yeah, there's all sorts of things to wonder about this picture, but the picture seems pretty appealing. There's tons of stuff.
Potentially. I really need to think about this a lot more, but potentially it could be very nice. All right. I guess I'll go home and think about this stuff. So this was great. Thanks a lot.
Okie doke.
I just need to think about this one.
Yep, I'll see you next week then.
Okay, I'll see you next week.
Okie doke.
Bye.
Great, bye.